Hey guys, Mr. Betts here. In the last topic, we talked about a variety of ways that we can apply calculus and derivatives to real world type functions. This topic, we're going to spend more time talking specifically about motion of objects, specifically motion of objects along a straight line. So, a lot of times we'll be talking about something moving along like the x axis, or we might say along the y axis. The important thing is it's along a straight line. So we could think of it as a car driving down a road, but we're not talking about motion in two dimensions, just in one dimension, moving forward or moving backwards. And we're going to be looking at the position of an object, so where the object is on that number line. We could even think of the road as a number line with mile markers on it, and how we connect that position to the velocity of the car. And speed. We're going to talk about velocity and speed. Those are two separate things that are closely related, and acceleration. These are all ideas that even if you haven't taken physics, you should be a little bit familiar with. Even if you're just thinking of it in terms of driving a car, it's a lot of it is pretty intuitive, and you should hopefully be able to grasp it pretty quickly. So in these problems, we're going to have some sort of function that is the position. So in this case, I'm going to call the position x. So we might be talking about moving along the x-axis. Notice that the x-axis is actually the vertical axis in this example. So the function is going to be x with respect to time. So the function itself is going to be the position of an object, and the independent variable is going to be how much time has passed. When we take the derivative of a function like this, we get x prime of t, or in differential notation, we'll say dx dt. I like the differential notation because it helps with units. So the units along the x-axis are meters, and the units along the time axis are seconds. So we get meters divided by seconds, or we can say meters per second. So when we take the derivative of the position of an object, we get units that are meters per second. And meters per second are units that we use to tell how fast something is moving. So if something is moving 2 meters per second, that means every second that passes, that object's moving 2 meters. If it's moving 3 meters per second, it's moving 1 more meter each second, so it's moving faster. So meters per second is going to tell us how fast something is moving, which is going to be what we call velocity. If we take I don't want you to confuse this as meters per second divided by velocity. So this is going to be velocity. The second derivative, we can say x double prime of t, also d squared x over dt squared. That's our second derivative notation with differentials. And essentially what we're going to do is divide by the horizontal units again. So we get meters per second per second. So this isn't maybe quite as intuitive, but remember, meters per second is telling us how fast something is going. So this is telling us how fast that velocity is changing. So when we take the second derivative of position, we're taking the first derivative of velocity. And so the second derivative is telling us how fast that velocity is changing. So the meters per second, which is velocity, is changing each second, so per second. So if this is a positive value, the velocity of our object is getting bigger as we go along. So this is what we call acceleration. So we're going to get into what velocity and acceleration are a little bit more depth and how we interpret those. But it's important that we understand if we take the derivative of position, we get velocity. And if we take the derivative of velocity, we get acceleration. So we could say x prime of t equals v of t. So v represents velocity. We could say that the derivative of velocity is acceleration, and that's the same thing as taking the second derivative of the position. So these relationships are really important to understand. And we also need to understand that these instantaneous rate of changes can be positive or negative. So if we're talking about velocity, if the velocity is positive, that means that the change in position is positive, and that means that the object is moving in a forward direction. Now, I put forward in quotation marks here because it depends on the context. If we're on the x-axis, forward is going to be to the right. If we're on the y-axis, forward is going to be up. So the important thing is the position is increasing. If we're driving on the interstate highway, we might say forward is where the mile markers are getting bigger, where that might be a little different than typical, where we say forward is where the car is actually moving forward. From a calculus standpoint, we're looking at it in terms of a number line, so where the numbers are getting bigger. If the velocity is negative, then we would say we're moving backward. Again, the position is decreasing, so moving to the left on the x-axis or moving down on the y-axis, or mile markers are getting smaller. So the position is getting smaller, so we're moving backward. If the velocity is 0, this means that we are not moving at all, at rest. So we could say at rest or not moving. And so we could think of this as, let's say we're in our car, we're moving forward in the car, and we put it in reverse and we start moving backwards. I definitely would not recommend putting your car in reverse while you're moving forward, but you get the idea. That moment where you change from moving forward to moving backwards, there's an instant there where you're not moving at all. So this would be where the velocity is 0. You could also think of this as tossing a ball in the air, and that moment where the ball stops moving up and starts coming back down, that instant, the ball is not moving at all. So the velocity is 0. If we look at this in terms of acceleration, if the acceleration is positive, remember acceleration is the derivative of velocity, so that means that dv dt is positive. And so that's telling us that the velocity is increasing. Now, it's really important that we don't misinterpret the velocity increasing as going faster. It might be tempting to think that this means going faster, and sometimes it does mean going faster. But if the velocity is negative, if we're moving backwards and the velocity is increasing, the velocity is actually getting closer to 0, because velocity is negative but getting bigger, it's getting closer to 0. That actually means that we're slowing down. So right now we're just going to say a positive acceleration means that the velocity is increasing, or a negative acceleration means that the velocity is decreasing. But whether or not we're speeding up or slowing down depends on if the acceleration is positive or negative, and if the velocity is positive or negative. And we'll get into that in a moment. If the acceleration is 0, that means that the velocity is not changing. So we could say velocity is constant. Now, again, like when the velocity was 0, this might just happen for an instant. So it could be where you're accelerating, you're going faster and faster and faster, and then you stop accelerating and you start decelerating, which is just negative acceleration. At that moment, the velocity is not changing. So if you're in your car and you're accelerating and then you let off the accelerator and you start slowing down, there's a moment there where your velocity is no longer going up and it's not going down, and the velocity is constant. So that would be what happens when the acceleration is 0. So let's look at some specific examples. If the velocity is positive, that means we're moving forward. And if the acceleration is positive, that means the velocity is increasing. So those two together, if we're moving forward and the velocity is increasing, that means that we're going to be speeding up in a forward direction. Sorry about that. If, on the other hand, the velocity is positive and the acceleration is negative, that means that we're moving forward, but the velocity is decreasing. So if we're moving forward, the velocity is positive but getting smaller, this actually means then that we're slowing down. So we're still moving forward, but we're slowing down. So we could think of this as going forward in our car, but hitting the brakes to slow down. If the velocity is negative, that means that we're moving backwards. So we're in reverse in our car, but the acceleration is positive. So the velocity is increasing. This is a little counterintuitive here. So we're moving backwards, but the acceleration is moving forward or increasing our velocity. So what's happening here is if our velocity is, say, negative 20 miles per hour, that's going backwards pretty fast. If the velocity is increasing, then it's going to go from negative 20 to negative 19 to negative 18. So our velocity is getting bigger, but it's getting bigger closer to zero. So if we think of the graph of our velocity here, if we're moving backwards, our velocity is negative and our acceleration is positive, that velocity is getting closer to zero. So we're actually slowing down still. So we're moving backwards and we're slowing down. So a positive acceleration here would be like if we're in our car, we're in reverse and we hit the brakes, we're slowing down. Okay, the last option here would be that we're moving backwards and the acceleration is negative, which means the velocity is decreasing. So in this case, if the velocity is negative, say negative 20 miles per hour, and the velocity is decreasing, it's going from negative 20 to negative 21 to negative 22. So the magnitude of our velocity is getting bigger, and we're actually speeding up. So whether we're speeding up or slowing down, this is the idea of speed. So speed is just how fast we're moving. So it's important to understand that velocity is what's called a vector and speed is what's called a scalar. And we'll get into that a little bit more later, but velocity tells us how fast we're moving, but also how quickly we're moving in that direction. And speed just tells us how fast we're going. So this is just kind of a summary. I do have an empty line down here because there's actually a bunch of other options. If we start including zero, so if we say the velocity is positive and acceleration is zero, that means the velocity is not changing. So we're not speeding up, we're not slowing down, we're just moving forward. We could say that velocity is negative and acceleration is zero. So again, velocity is not changing. We could say the velocity is zero, but the acceleration is, say, positive. So if the velocity is zero means we're not moving, but the acceleration means that we're about to start moving in a forward direction. So we're speeding up and beginning to move forward. This is kind of a weird one to think about, but if the velocity is negative and velocity is zero and acceleration is negative, again, we're not moving. We're about to start moving in a negative direction because the velocity is decreasing. And so we're actually speeding up still. So if the velocity is zero, no matter what acceleration is, we're either just sitting still or we're speeding up. Okay, a car's not moving. So whatever direction you move, your speed is going to start increasing. So we're going to be speeding up, but we're speeding up in a negative direction. So velocity is, remember, it tells us how fast we're going, but also if it's positive, it tells us we're going forward. Negative tells us we're going backwards. Speed in this case is just going to be the absolute value of the velocity. So if we're moving forward 20 miles per hour or moving backwards 20 miles per hour, our speed is just 20 miles per hour. Velocity is going to be positive or negative, telling us what direction we're going. So velocity, again, is what we call a vector, which has a magnitude, the magnitude being the speed, and the direction being positive or negative, where speed is just what's called a scalar. It's a magnitude only, and the speed is the absolute value of velocity. One other big idea here real quick, displacement versus distance traveled. So displacement means pretty much literally what it says. Displacement means out of place. So displacement is a measure of how much out of place something is, or how much something has moved from where it started. So if we have an object that starts at one point, it moves a little bit, it moves back a little bit, and ends up here, the displacement is just the distance from where it started to where it ended up. Displacement is a vector. So if it ends up further to the right than it started, then it's going to be positive. If it ends up further to the left, then it's going to be negative. Distance traveled, on the other hand, if we have an object that moves and then it moves again and ends up here, the distance traveled takes into account all of that motion. So it adds this distance and this distance together. So imagine you start at Belleville West and you run south on Frank Scott Parkway to the stop sign at Concordia, and then you run all the way back to where you started. The displacement would be 0, and the distance traveled would be 1.5 miles in each direction. So you ran a total of 3 miles. So the displacement of 0 does not really indicate how much work you put into running 3 miles. So distance traveled is going to be important to us sometimes in knowing how far we actually went. So the displacement is the distance between positions at 2 different times. It's a vector that we just get by subtracting the final position minus a starting position. And distance traveled is like, if you think in your car, an odometer distance. If you start at school and you drive south 1.5 miles and then north 1.5 miles, the odometer has increased by 3 miles, even though the car is where it started. I do want to point out that these are often different, but if an object does not change directions, they're the same. So if we drive 1.5 miles in one direction, our displacement is 1.5 miles and our distance traveled is 1.5 miles. Once we change directions, then we have to look at the distance traveled as displacement between points where we change directions. So we can think of distance traveled as our displacement in one direction plus our displacement in the other direction, and thinking of it as a magnitude or an absolute value.